In dynamics, we study the interactions between objects, which we call forces. Newton's second law tells us how one object responds to the interactions that it experiences. But we're going to turn our attention now to looking at more than one object at a time, how multiple objects interact and move. And for that, we need Newton's third law of motion, N3L for short. And we'll introduce the concept of force pairs. Now, you're already familiar with Newton's third law. Most everyone is. Even Joey Soft-Moroni here could give us the layman's version of it, which usually goes like, for every action, there is an equal and opposite reaction. That's basically Newton's third law, but I feel like this wording is kind of misleading. Most textbooks will use the terms action force and reaction force, but that's not really accurate. That makes it sound like one force is the cause and the other force is the effect. But that's not what really happens. When two objects interact, they exert forces on each other simultaneously. There's not a cause and an effect. Both forces happen at once. So for that reason, I think this is a more accurate statement of Newton's third law. When any two objects interact, they exert equal and opposite forces on each other. So here we have two objects, 1 and 2, different sizes, but clearly they're repelling each other, interacting by pushing each other apart. And I'll introduce some notation here. F12, subscript 1, 2. By that we mean the force on object 1 due to object 2. Likewise, this would be the force on object 2 due to object 1. Newton's third law is asserting that what we always observe in nature is that the force on 1 due to 2 is equal in magnitude but opposite in direction to the force on 2 due to 1. Now, there's a bit of fine print here. Newton's third law also tells us this. Every interaction that we see in nature is always either this type or this type. Always the objects either pull each other directly together or push each other directly apart. We never see this sort of interaction in nature. These two forces are equal and opposite, but they're not directed along the line connecting the two objects. Newton's third law asserts that this is forbidden, apparently. Every interaction is always either this or this. Now, as the story goes, Newton discovered the third law of motion, his third law, during a football riot. If you'll examine this historic photo from the year 1662, taken at a match between Manchester United and Arsenal, and look carefully, you'll see this big-haired fella right here throwing headbutts. That is a young Sir Isaac Newton. As an Englishman, he was a great fan of the game and also fond of hooliganism. What Newton learned pretty quickly, though, in all those football riots, is that when you throw a headbutt, it's not like in the movies. If you go forehead to forehead with your opponent, nobody wins. You get hit just as hard as the person you hit. This gave Newton the idea of force pairs. So here, if we've got a little FBD for Joey's head and an FBD for Newton's head here, just looking at that interaction during the attack, the force on Joey's head due to Newton's head is equal and opposite to the force on Newton due to Joey. They're going to feel the same force when their heads collide. And in that sense, nobody comes out the victor. At least not until Newton learned to modify his attack technique. If instead of going forehead to forehead, if Newton strikes at the bridge of Joey's nose, then he takes advantage of the differences between these parts of the skull. Now, a forehead will require 2,000 newtons of force to fracture it, but the nose bone here, the nasal bone, requires only about 500 newtons to do the same. Thus, Newton learned that if he throws a headbutt at about 1,000 newtons of force, they'll both feel 1,000 newtons, but Newton's forehead will be fine, while the nose will be quite destroyed. Let's look at some other examples of force pairs. Suppose Newton is escaping from just such a riot, and he's running across the rooftops of London and perhaps passing along a beam between two buildings, where he pauses for a moment to catch his breath, feeling a bit dizzy. And as he's standing there, his free body diagram looks like this. There's a normal force upwards on Newton, balanced by the force of gravity pulling downwards. This is Newton standing still. Now, these two forces are equal in magnitude in opposite direction, while Newton's here in static equilibrium, but they do not represent a Newton's third law force pair. Let's be very clear. The two forces in an N3L force pair have to act on two different objects. So if we want to find the other object that's involved in this interaction right here, we look at the surface. It's the surface that's pushing upward on Newton. Therefore, Newton is also pushing downward on the surface. That's why the beam is sagging here. So the force on Newton due to the surface is equal and opposite to the force on the surface due to Newton. That is a Newton's third law force pair. To find the corresponding force to the force of gravity on Newton, we have to look at the object that's exerting that force of gravity on Newton. And it is the entire planet Earth. We'd have to zoom out to see that just as the Earth is pulling down on Newton with this force, little Newton here is pulling upwards on the entire planet. His own mass is pulling upwards on the mass of the Earth with an equal and opposite force. So there is an N3L force pair as well. Example 3. Suppose you're walking or driving along. In order to take a step, in order to propel yourself to the right across the floor, you need that static friction, that traction between the floor and your foot right there. So that would be this force on Newton due to the surface, that's static friction, pushing Newton to the right. But at the same time, Newton's foot would be pushing backwards on the floor, a force on the surface due to Newton. There's your equal and opposite Newton's third law pairs. And that's easiest to imagine if you picture Newton walking across a rug here and him pushing the rug backwards as he moves. Say this is our rug. We come walking along, stepping onto the rug, pushing it backwards as it pushes us forwards. Similarly, riding a bicycle or driving a car, the force of static friction between the ground and the wheels, that traction, that's the force on the wheel due to the surface. That's what pushes the bike forward. But at the same time, the wheel, the tire, where it contacts the ground, is pushing backwards on the ground. The force on the surface due to the wheel, that's an equal and opposite Newton's third law pair. And that you can visualize if you imagine the bike moving along, say, a ground covered with gravel and the wheel kicking up gravel, pushing it to the left as the bike moves along. That's that corresponding leftward force in that third law pair.